Hi and welcome to the second section of this course. In this section, we'll discuss how to deal with the text data, and this video in particular starts from tokenization, which is the process of breaking a text down into tokens. Before we start digging into the details of tokenization, let's have an overview on the section. We'll learn practical aspects of dealing with textual data. We start with tokenization, which is the process of breaking our text down into individual tokens. Then we'll discuss the pre-processing and cleaning steps that we need to carry out in order to prepare our data for further analysis. In particular, we'll see how to remove unimportant words and how to transform tokens into canonical forms. Lastly, we'll see how to compute basic statistics on our text so we can collect word frequencies. Now we are ready to start with this video on tokenization, going from documents to words. In particular, in this video we'll discuss the basic concepts of tokenization and we'll see how to apply it with data from different domains, specifically because different types of data might require different approaches to tokenization. And before closing, we'll also discuss how to capture phrases rather than individual words. So as a broad definition, tokenization means breaking a raw string down into a list of tokens, but now the question really is what constitutes a token? So it's quite straightforward to think in terms of single words, but then how about phrases? Sometimes concepts are described using more than a single word, and when breaking things down, we quickly see that there are also many types of tokens that could require special treatment depending on the application, so it's important to be aware of that. For example, punctuation symbols are special tokens, and so are numbers, dates, or currencies. Some specific domains, like social media, could have also special tokens that we don't normally see in natural language, like for example hashtags. The list could probably continue, but now you have the flavor. For this section, we are going to use the library called NLTK, or Natural Language Toolkit. It's one of the many libraries for natural language processing in Python, and it's an excellent teaching tool. For more advanced applications, there are also other options to consider, but for the kind of pre-processing steps that we're going to see in this section, NLTK is a good choice. You can check out nltk.org to read more about NLTK, and if you have followed the installation and setup video, you should already have installed the library in your virtual environment. If you haven't, you'll just need to activate the environment and type from your command line conda install nltk. But please check out the installation and setup video for all the details. NLTK also comes with a bunch of additional resources, in particular data of pre-trained models to perform some particular operations. There are a few options to install the additional data, and if you check out the webpage nltk.org/data.html, you can read more about this process. One of the ways to install the data is to call the NLTK downloader from the command line using the command python -m nltk.downloader, followed by the names of the packages that you want to install. Some of the packages that we'll need for this section are punct for tokenization, stopwords to get a list of English stopwords, and wordnet, a lexical resource to perform some of the text normalization steps. You could also use the alias all to install all the packages, and this will download about 2 GB of data. So if disk space is not a problem, you could also go in that direction. So after NLTK and its data are installed, we're ready to dig into the code. Let's start with a simple example. Let's say we have a string representing a sentence, in this case the classic "the quick brown fox jumped over the lazy dog." So why not just using the split method, which is part of the string object? By default, it splits a string based on white spaces, and it returns a list of the individual words. Now the reason for not using it is quite simple. In fact, as soon as we have punctuation in our string, this will be ignored. For example, if you notice the comma after the word fox, you will see how using split will fail to perform tokenization properly in this case. So to tackle this problem, we start using the NLTK library, and in particular the tokenize package, which comes with a word tokenize method. This function currently uses a method based on regular expressions to break a string down. So as we can see with the previous example, the word fox and the comma are correctly split. So now the comma itself is an individual token in the output list. Punctuation, anyway, is not always split. For example, here we have a person name with a title, Dr. Smith, and in this case it makes sense to keep the title together, so the dot is part of the same token as the abbreviation for doctor, like so. One more example. Here we have not only abbreviations like VS for versus, but also acronyms, which are sometimes represented using the dotted version like USA on the right. In this case, the acronym is only partially kept together, so the last dot is considered to be the full stop at the end of the sentence and split from the rest of the acronym. On the other side, if the acronym is in the middle of the sentence, so after USA we have more words, the acronym USA itself is kept together with all the dots correctly. Next, let's look into sentence tokenization, also called sentence segmentation. Sometimes our string has more than one sentence in it, like in this example. And using word tokenization directly, we produce a single list of tokens, with the full stops being part of it, so there is no clear distinction between different sentences. Luckily, NLTK also offers a function for sentence tokenization called send_tokenize. Given a string, the output of this function is a list of sentences. So at this point, we have a clear separation of sentences, and each sentence can be passed individually to the word tokenizer for further processing. So in this last example, at the end we have a list of sentences broken down into a list of tokens, like so. What we have seen so far works well enough for the general case, or if you prefer, for general purpose English. Sometimes we are dealing with a particular business domain with data that require a slightly different treatment. So let's consider the popular case of data mining for social media. And in this example, we have a string which could be taken from Twitter. Of course, it's not a real tweet, but it shows how the data can be different from general purpose English. So here we have a user handle with the @ symbol at the beginning. Then we have an old style ASCII emoticons, a URL, and finally an hashtag. Using the function word tokenize directly simply breaks everything. So the user mention and the hashtag symbols are split, and also the emoticon and the URL are broken down incorrectly. So the solution in this case is to use a specialized tokenizer which is able to handle the peculiarity of the specific domain we're dealing with, Twitter in this case. And NLTK also offers a tweet tokenizer class which implements a tokenization algorithm suitable for our purpose. The interface is slightly different in the sense that we need to make an instance of the tokenizer first, and then we call the tokenize method on it. But the output is still a list of tokens, and as we can see here, the tokens that were broken down incorrectly in the previous example are now split as they should be. So the overall message is that for some domain-specific applications, you might need to find a tokenizer which takes care of your specific type of data. For the last part of this video, we look into phrases. So far we have considered only tokens as individual words, but sometimes it's also interesting to look into phrases so we can capture concepts that are expressed using more than one word. For example, the quick brown fox from the previous example, and let's say good movie or nice restaurant if we are analyzing some reviews. So given a sequence of tokens, or more in general a sequence of items, we use the term n-gram referring to a subsequence of n terms. Common cases are n equals to 2, and this is called bigram, or n equal to 3, and this is called trigram. And NLTK offers some function to quickly get n-grams from a list of tokens. So for this example, we first import all these functions, bigrams, trigrams, and n-grams. They all require a list of tokens as input, and they produce a generator as output. In order to get the n-grams from a sentence, we need to tokenize it first and then pass the tokens to the appropriate function. So here we cast the bigrams as a list so we can force the evaluation of the generator and see the actual bigrams on the screen. As we can see, bigrams are given as tuples of two elements, day quick, quick brown, brown fox, and so on. The next example shows trigrams. It's very similar to the bigram example. We simply have tuples of three elements as output. Both these functions, bigrams and trigrams, are really shortcuts for the general purpose function called n-grams, which takes also a second input, the size of the n-gram itself. So in the last example, we are still creating bigrams using the n-grams function with a list of tokens and finally the number 2. And the output is the same as you can see here. So in this video we have discussed tokenization, which is the process of breaking a raw string down into individual tokens. We have also discussed the problems of sentence segmentation and how to deal with data coming from different business domains, for example Twitter data. And finally we had a look into n-grams in order to capture phrases besides individual tokens.